Hello, our names are Amara and Isa, and this is our final project for CS 2316. For our project, we have decided to analyze the relationship between an urban area's walkability score and its average air quality index. A city is walkable when residents are able to reach their final destination through walking only. We chose this topic because we are interested in how climate conditions affect our daily lives and how urban planners can take precautions for reducing carbon emissions to combat climate change. We decided to look into the 50 most populated urban cities and determine if there was a link between a city's walkability score and the average air quality of that location. We hypothesized that cities that have a high walkability score have a higher average air quality and higher socioeconomic status because these communities have the financial means and are making a conscious effort to pivot towards climate-friendly transportation solutions. We analyzed information about the specific type of pollutants that contribute to air quality and how these concentration values affect the overall health of a population. We also interpreted socioeconomic data to determine the population demographics of individuals who live in areas with a higher walkability score.
Our first data set is a downloaded CSV file from data.gov that contains population information for CBSA tracts in the United States. CBSAs are geographical areas that consist of one or more counties anchored by an urban center. The data set contains specific population information such as number of employed individuals, employment type, and types of housing, as well as National Walkability Index, a value between 1 and 20, with higher values indicating greater walkability for each CBSA tract. After finding the walkability CSV, we thought it would be interesting to find information about air quality and air pollutants in urban areas and correlate this to the walkability index. We used the EPA's API containing specific concentrations and counts for common air pollutants per CBSA tract. Finally, in order to connect these pollutant counts to a health indicator, we found a table on the Air Quality Index Wikipedia page that contained air pollutant thresholds that correspond to specific air health values.
To clean our CSV data, we used the pandas module. We used masking techniques to only access the specific columns that we wanted. To correct an inconsistency in the dataset regarding repeated or missing city names, we decided to group by city name and aggregate each column by the mean value. We corrected another inconsistency in the column titled D4A, indicating the number of miles from a population center to the nearest transit stop. We used the pandas.where function to replace the filler value negative 99,999 with the string representation too far. Correcting this inconsistency allows for us to see a general too far value for cities that do not have easy access to public transportation as opposed to cities that do. We also sorted by the descending population and indexed the first 50 values.
To streamline the data cleaning process for the API, we separated the cleaning into methods for each pollutant we were interested in. We read in the CBSA codes for each city from the walkability.csv created from the CSV downloaded dataset and used a for loop and an f-string to make a request to the URL that was constructed to go through each city for the specified pollutant. We used the .json method to convert the JSON response data into a Python object and then appended the desired data, city, sample duration, observation count, and units of measure to a dictionary. However, some of the CBSAs for certain pollutants had no data, so we created an if statement to ensure data existed before attempting to append it to a dictionary.
To begin cleaning our HTML data, we made a request to the Wikipedia page and we used the Beautiful Soup module to parse through the dataset and extract the specific table that we needed. In the table on the website, there were 2 incomplete separate columns for ozone collected over different durations of time, so in order to maintain consistency, we decided to combine these columns and convert all ozone data to be over a 1-hour duration. Finally, at the end of our cleaning, the last row and last column, AQI health rating, contained missing information, so we used .iloc and pandas to replace the empty value with hazardous.
For the first insight, we wanted to assign each CBSA tract a label based on its walkability index. From there, we wanted to sort each CBSA tract in order from the city deemed most walkable to the city deemed least walkable. We used the .mean and .standard deviation panda aggregate functions to find the average walkability index and the standard deviation for this column to initialize an upper/lower bound for comparison. We deemed cities to be least walkable if their walkability index was 1 standard deviation below the mean, moderately walkable if their walkability index fell between 1 standard deviation below the mean and 1 standard deviation above the mean, and very walkable if their walkability index fell 1 standard deviation from the mean value. According to the mean value 10.746, the average walkability index for the top 50 most populated CBSAs in the United States indicates that the average urban area in the United States is moderately walkable. The standard deviation value 1.59 is relatively low, indicating that the walkability indexes from the most populated cities in the United States has low variance from the mean. Our first visualization was a histogram that showed the count of CBSAs that contained a specific walkability value. From this visualization, we are able to see that out of the top 50 most populated urban areas in the United States, 8 are very walkable, 36 are moderately walkable, and 6 are least walkable. We decided to use a histogram because we wanted to look at the total count of CBSA tracts that had specific walkability labels.
For the second insight, we wanted to determine the correlation between the general socioeconomic status of an area and its walkability index value. We wanted to come to a conclusion about highly gentrified urban areas that have a high walkability score that boast markers of greater wealth in comparison to lower income urban areas that have similar scores. For our correlation calculations, we wanted to use the variables unemployment rate and percent low-wage workers. We calculated the unemployment rate for each CBSA tract by taking the total employment column values and dividing them by the total population column values. From there, we used the dot-core method to find the R values. From our calculation, we found that the correlation coefficient between the unemployment rate and the walkability index was R equals 0.44, indicating that there is a moderate association between a high unemployment rate and high walkability index. We also found the correlation coefficient between the percent low-wage workers and the walkability index to be R equals 0.18, indicating a weak association between those two variables. We determined this low correlation coefficient to be for a similar reason. There is a wide variety of socioeconomic areas within one CBSA tract. Therefore, there is a large distribution of income and labor. Our second visualization was a scatter plot that shows the relationship between the walkability index and unemployment rate. Each CBSA is plotted on the scatter plot, and we used a line of best fit to demonstrate the correlation between the two variables.
This insight was by far our most difficult to accomplish because we were trying to combine and compare information from two different data sets, the Wikipedia article and the pollutants API. We focused on two pollutants, PM 2.5 and PM 10, because of their overall harmful impact on air quality in urban areas. Based on this count, we consulted the scraped wiki table that displays air quality health ratings according to a defined upper and lower bound determined by the Clean Air Act. Through a series of conditional statements, we assigned each CBSA tract, PM 2.5 and PM10 observation counts to the Clean Air Act health rating. We assigned the value unknown to observation counts that were extremely out of range. From a health perspective, the dangerous air threshold for PM 2.5 is much lower than PM10 because of the more devastating health effects that finer particles have on long-term well-being. From a geographical perspective, many of the areas where PM 2.5 concentration is hazardous are areas where commercial vehicle industry is extremely popular.
For Insight 4, we also combined and compared two different datasets, the AQI Wikipedia and the Walkability CSV. We wanted to expound on our third insight by comparing the AQI health ratings for each CBSA tract to its walkability index. We sorted the data frame in descending order by walkability index and looked at the maximum and minimum values. Overall, our hypothesis was disproved, as there are unhealthy and hazardous values for PM 2.5 and a range of values for PM 10 throughout the entire sorted data frame. In fact, some of the only good health rating values came from CBSA tracts in the top 50% of walkability indexes.
For Insight 5, we used the API data and found a 5-number summary for each pollutant that we studied. In order to get these values, we used the .describe.loc method. We wanted to have a high-level overview of the pollutant information since most of our other insights focused on individual values per CBSA. From the summaries, we were able to see that PM 2.5 and PM 10 had extremely maximum outliers, and the rest of the pollutants had extremely minimum outliers. Our third visualization is a series of box and whisker plots. In the box and whisker plot, we made sure to include a point for each CBSA tract, so when hovered over, a user can see the specific observation count for each CBSA.
During this project, our greatest challenge came mostly from the API dataset. Calling multiple requests simultaneously was very slow and inefficient. We solved this by breaking up the data cleaning methods as well as driving back to our hometown to work on a stronger internet. Even after overcoming this hurdle, we then faced the issue that for certain pollutants, some city data was missing, requiring a very convoluted if statement. To recap our overall results, there is not a direct correlation between the walkability score of an urban area and its air quality. After exploring our datasets further, we discovered that there are a wide range of variables that impact the air quality of urban areas that are not related to urban planning. For example, we discussed that there are many highlighted CBSA areas that are deemed walkable but have large concentrations of air pollutant emissions due to these areas having large trucking, manufacturing, and commercial transportation sectors. Although walkability score can be a factor in the overall air health of an urban area, it is not the most important. We found that there was a moderate association between socioeconomic demographics and walkability. However, this correlation is not stronger due to the varied labor types and income levels within a singular CBSA tract. In conclusion, although the walkability score of a certain area can provide us with a lot of information regarding air health and population data, there are a wide range of variables, industry, and social factors that contribute to the overall conditions of a specific area.